Got a lot to discuss here. A lot of exciting work that we've recently completed, work that is ongoing, and excited to share it with you. So here I'm going to talk a little bit of the history. I want to put the work that has been in recent releases and that we're planning for a later release this year and beyond into some context. And then get into some details of what has been developed and why. Before I get to that, though, I do want to acknowledge the development team that we have here at CPFD. I'm very proud to be able to work with this group. Handles all the software development, the research and validation or testing, and of course support and training. It's a tight group, dedicated group with a lot of experience, and it's really their work here that we're talking about today. So this is a timeline here of Barracuda development. I think many have seen this before, but for those that are new, Barracuda was first released, Barracuda proper was first released in 2007, and over the years added chemistry, heat transfer, multi-component particles was a big deal, eventually expanded to Windows operating system, and then in 2014 was the first GPU release. Another big milestone in 2020 when we added TechPlot for Barracuda, partnership with TechPlot that we are thrilled about. It really upgraded the post-processing capabilities with Barracuda. And then just last year had our first multi-GPU release. Going forward, we're still continuing on multi-GPU development, and I'll talk about that, but also have shifted to a heavy emphasis on improving our vapor liquid solids capabilities, both for compressible simulations and incompressible. And so that was, first part of that was in our version 22 release last month, where we added multiple liquid chemistry capabilities, and then in the future we're working on discrete bubbles and the complexity that goes with that. Just wanted to overlay briefly the applications that we've seen, and this is not an exhaustive list. In fact, this was just pulled from some projects that I had done when I first joined CPFD. And really, I think it's interesting here is this point right here with the multi-component particles. This opened up a large number of new applications that were a challenge before. Going forward from that, these are not projects that I've done myself, but we're seeing here and done by others at CPFD, gasification, a lot of FCC regenerators. We've seen my talk here on cement and some of the new things with plastics recycling. And then what we're seeing in the future is simulations of ebulated beds and hydrocracking applications, and that is our target here with a lot of this work. There's a lot of other applications that are subsets of this when we start adding in bubbles, but this is one of our targets here. Before I get into all of that with the bubbles, I just wanted a brief perspective, my perspective on the GPU development over time. This is, we have this old model. It was developed about 10 years ago. It's this NETL, chemical looping combustion system. And at the time when this developed, this was put just about everything we could into this. Is full loop chemistry. Had this reactor riser, cyclone, loop seal, all these units, and this thing ran and ran and ran. When it was initially run in 2012, this took 82 days on a CPU. It was basically all summer. And this, since then, I've periodically pulled this model out. Now it's the cell counts, particle counts. Since then, they're quite modest by standards today, but still is kind of interesting because these are times we have runtimes here that are also being run on what was considered decent hardware at that time as well, along with the software. So a couple years later, with our first GPU release, this went down from 82 days down to 16 days, significant improvement there. Later, with additional parallelization and development of the software, it was down to 4 days. That's also, I think, there's questions about V100 numbers versus A100s. We start to see some of that here. So software improvements, but also significant hardware improvements. 2019, there was a significant here with GPU chemistry was added, and we're down to 2.5 days. And then now with 21.1 on an A100, the same model's now running in under 16 hours. So, I mean, 10 years, it's been a lot of time, but significantly different and improved runtimes, we'll say. Just a couple other things on the multi-GPU. For the version with multi-GPU support, so this was first version 21, there was a significant changes to the underlying memory handling. And this took a long time. I think we talked, some of our customers, we've been hearing about, oh yeah, we're working on it for a long time. But as a result of this, even for a single GPU, with the new solver and these changes, it was running about 2 times faster than the previous on same card, same model. And we are seeing, particularly on larger models, we're seeing positive scaling up to 4 GPUs. And there's much more information that is going to be presented later, I think, by Sam. Sam will cover this a bit more detail. Another important thing that came out of this is that oversubscription of the GPU memory is possible. It used to be before you were limited by the size of the amount of memory on the GPU card. If you have a lot of particles being fed in, you go over that memory now, it will not do a fallback to CPU or crash if sometimes the case. And it's not recommended. There is there's a bit of a penalty in terms of calculation speed when oversubscribing, and so it's much better to make use of an additional GPU card if that is an option. One other thing I just want to say on this is that we did benefit greatly from collaboration with NVIDIA during this development. We had some NVIDIA engineers who were looking at the code, discussing how to best parallelize some of our rather complicated functions, and I think the speed ups we're seeing as a result of that collaboration is, we're seeing it in the data now, and just the one talking about the hardware versus the software improvements. One point, because we've got more colleagues that have, particularly Andrew Larson, who unfortunately could not be here. There's been a tremendous amount of effort going into the development of the GPUs, and we are making Barracuda be able to take full advantage of the GPU hardware. And we did this analysis back in 2018. It was actually running that same chemical looping model because it was for a chemical looping conference, and just showing both changes in hardware and changes in software versions. And just roughly, it's about a 50-50 kind of contribution, both in hardware improvements and then the corresponding software changes to take full advantage of that new hardware. Going forward, work is continuing on the multi-GPU. Every time it gets faster, the code gets faster. It's a new bottleneck. What's the new bottleneck? What's the next thing to make more efficient? And sometimes these are kind of funny. It'd be like, for a while, flux planes were taking an inordinate amount of time in the calculation. It had not come up until that point, until everything else was significantly faster than the flux planes code. We are trying to get beyond 4 GPUs in an efficient way, and so that's something we're continuing to look at, along with some other parts of the code that have just not gotten as much attention and weren't as important until now, when they're starting to stick out. Things like gas tracers, and we'll be continuing to look at the chemical reaction solvers, which are also starting to stick out. So that was just the perspective I wanted to add on the GPUs, and switch now over to the vapor liquid solid development. So in version 21.1, just kind of get a sense of what our starting point is here. Okay, for gas solid systems, or in the GUI referred to as compressible models, we do have liquid droplets. That was capability. These droplets could coat, and it's like Frederick's presentation today mentioned used some of that feature. What the limitation with this, though, is that the liquid film, there's no liquid film chemistry. It was in a sense a dead end for these any compounds could go. Really, the only option was the evaporation model, which had been in beta for quite a few years. On the liquid solid simulations, the incompressible simulations, in 21.1, you could only have a single fluid, single component in the fluid phase. So there were no reactions. There were really, it's just useful for things like settling, solid settling simulations. So that was the starting point. When we started thinking about development for ebulated bed models. And what an ebulated bed, for those that aren't familiar, is essentially a 3-phase system where you have, at least modeled within Barracuda, you'd have a liquid, a continuous phase, a discrete solid particle phase, and then discrete bubble phase. The bubbles being like hydrogen gas being injected. And to calculate these bubbles, the discrete bubbles here, being careful to separate them from bubbles that we'd see in a fluidized bed. This can be a point of confusion at times. We're talking about gas bubbles within a liquid system. The attraction here is that we can simulate these using the same underlying code that we calculate all the particles with. Of course, bubbles are quite different from particles in many ways, and so work here to add new physical models and in some cases concepts to the software, and this is then this is included in our recent version 22 release and then in the upcoming ones. And so my point here is to provide some context for the features. Sam will be discussing some more of that in detail later, but this is how it's all tying together. This is our target on for these ebulated beds. Just an example of a demonstration here this would be a LC fining hydrocracker. This is all obtained from open literature, and in some cases some estimates made on some dimensions, but showing it here to illustrate again what we're talking about, where we have a large unit, solid catalyst in there, liquid solid bed with, and we have gas bubbles being injected at the bottom, passing through a distributor plate, and the liquid being recycled through the top back to the bottom, and hopefully some separation of the liquid and gas at the top. To be able to model this, it was helpful to look at the necessary kind of physical models from the standpoint of the hydrogen bubble, and I've started to underline things that we could not do in version 21.1 to kind of get our punch list for development. So just starting we've got a pure hydrogen bubble being injected below a distributor. So right off the bat, okay, we need discrete bubbles. This hydrogen would be diffusing into the liquid through like a gas absorption model. So thinking like a Henry's law constant, describing that equilibrium. And it's diffusing into a liquid that is composed of multiple reacting components, where the liquid is being cracked in this case. Oops, sorry. The bubbles then passing through a distributor. This is something we, at that time, were not able to do, where then this hydrogen is reacting along with the solid, on the solid catalyst in this liquid phase, producing now multiple liquids, multiple liquid components within the gas phase, within the fluid phase. As the reaction is progressing, we have now products that are liquid vapor products or gaseous products that are diffusing back into this bubble. So the composition of this bubble is changing as it's traveling up the reactor. And so when we combine all of these, we start to get our punch list of new development required to support this application. And so and at the same time, taking the opportunity to finish some of the compressible models. So we added liquid film chemistry in version 22 for compressible simulations. We introduced vapor as a phase of matter in Barracuda calculations, and I'll explain that a little bit more. Release and a revamp of the evaporation model for compressible simulations, adding multiple liquids, multiple liquids within the fluid phase of an incompressible simulation, fluid phase reactions within an incompressible. This concept of particle bubble filtering at baffles. So we could use a baffle as an internal distributor plate where we'd have transport in one direction only. This is all part of version 22 that was released just last month. Going forward, we're planning a release in the October timeframe of version 22.1 that would include discrete bubbles and all that is associated with that. So this is a buoyancy matters in this case. It's actually just in general forces that were fairly negligible for particles matter a lot in bubbles. So there's some stability improvements that were added, actually included in version 22 that fix some long-standing stability issues in liquid-solid simulations, adding concepts of bubble compressibility, surface tension, lift force, and virtual mass force. Don't matter much in a typical gas-solid simulation, but have about 1 million times greater impact on a bubble in a liquid bed. So all of that, along with bubble liquid evaporation, a gas absorption model, and then the beginnings of a decoupling of particle and bubbles at close pack. And so I'll talk about some of these things in more detail here. So I'll move through some of these quite quickly. They're in release guide materials. They're in webinars, and there's other sources with much more information. My purpose here is to connect these features together and make you aware that they're there. So compressible models, said it a few times, liquid phase chemistry, and then an actual release of the evaporation model. See here, this resulted in or required a overhaul of our base materials GUI because we needed to introduce this concept of vapor and not right. Okay, yeah. So in previous versions of Barracuda, evaporation was, well, there was only three phases. There's a gas, a solid, and a liquid. And an evaporation model was essentially a transfer between, or an equilibrium between a liquid and a gas. As soon as we start introducing concepts of gas absorption, where we have gases that are not in equilibrium with a liquid, but are dissolving into a liquid, we have conflicts now of that we're trying to apply two different models to the same a pairing, and it just became a mess. So we said, okay, we got to separate this. We're going to call a gas, a vapor, introduced this phase, and made sure that everything was backwards compatible for existing models that were using the old beta evaporation model. So now in the GUI we see there's some complexity here in being able to select a liquid or have a vapor component to it, and the heat of vaporization and vapor pressures and everything being connected within the model. The multiple liquids and incompressible then gases that could be dissolving into these liquids. It did require a complete rewrite of our pressure solver to be able to support this. And nice thing here is the results were very, very minimal or negligible changes in any computational results, but as a result of this, this pressure solver does run quite a bit faster than it did previously. Incompressible liquids, same interface, should be very familiar to anybody doing reactions in a compressible model. And then the particle filtering that I mentioned before, where we have, this is now a feature of the baffles, where you can have basically directionally determine whether a particle or bubble or droplet can be traveling upwards or downwards, and whether it can pass through baffles. So part of our recent efforts to make these baffles a more powerful component within the model. So that, I mean, for version 22, that was the significant development there towards the ebulated bed as an application. And now moving on to what is expected and is in development for version 22.1. And so the main thing here is a discrete bubble, which is, hey, okay, good, it worked. Is can be composed of gases and vapors. Its size will be changing as the simulation goes as a function of pressure, temperature, surface tension, any compositional changes within there. Lift force and a virtual mass force have been added. They have a significant impact, and inclusion of surface tension allows us to be adding more or appropriate drag models for bubble swarms that are a function of surface tension and bubble size and all of these things. So here's just a video of some of our ongoing validation efforts comparing against some of the bubble column data that is available. And then one of our areas in the future I'll talk a little bit about is how do we handle bubbles at close pack, and how is this different or similar to particles. The other piece that is coming, it's implemented, looks great, is gas absorption, and where we have discussed so for example, hydrogen moving in liquid phase or vice versa, an equilibrium determined by Henry's law constant that can be input in the software, and then determining the mass transfer rates, the Sherwood number using some correlations for bubble swarms, and then a diffusion coefficient being estimated from a Wilkie chain correlation. So we're trying to make sure these are things where models where the inputs are actually answerable. You can look up things in either literature or in a reference and input them into the software. And the result of this here, demonstration and showing the change in bubble composition here, as a function of the elevation within this ebulated bed. We have high levels of hydrogen at the bottom, slowly being replaced by other components that are being produced by the reactions. Last thing I want to talk about, and this is starting to push up against limits of where we are at right now with this development, and is the handling at close pack. This has been a long-standing request from people that we have species-specific values for close pack volume fraction, and we have added this. It is in beta in version 22. It is a local close pack volume fraction that is calculated, so cell by cell basis, depending if this, or using the species value if it is defined here within the GUI, and the local close pack being calculated as a function of the volume of the particles present and whatever that specified close pack volume fraction is. If this isn't specified, then the global value is used. But this, again, this is kind of pushing up against of where we're at and things that we're going to be continuing to look at and validate in the future. And it's just getting into other important things that are in important nature of bubbles. And so things like bubble splitting, coalescence that are going to are significant in many cases. And then I think we do need to keep looking at, or definitely need to keep looking at the handling of bubbles at close pack, or essentially foam at that point. And we know it's complex, and this is just a very simple experiment actually done at home that I think illustrates all of this together. This is, I am in my free time, I brew beer, and I had a particularly foamy keg here that I could just do some experiments here. So, filled up a cylinder with foam, and then based on measurements of the top and bottom and where the levels were of both the liquid and the height of the foam, could back calculate what the volume fraction of gas in that foam is in time. And what we see is, well, we know, anybody that's done this experiment themselves in a glass knows that it is changing. What was interesting is that, at the start, things were right around 65% gas, and the rest being film and beer within it. But over time, this increased actually to quite high levels where I think this will start to be considered more of a dry foam than a wet foam. Just sitting there, right? And we could, observing it, see, okay, this is coalescence happening, and then also this increase due to the polydispersity of bubble sizes within there. It started out everything visually quite uniform, and then you start getting bigger ones, smaller ones in between. So just presenting this just purely is to highlight, yeah, this is where we will be working beyond getting kind of the basics in place of what is a bubble, can we calculate it, and this type of stuff. So in summary, there's a lot of exciting development that we've been doing recently. Of course, the major speed up in the calculations in our recent releases, and then the ongoing development targeting ebulated bed and other discrete bubble applications. So with that, I thank you and happy to take any questions.